You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Network controls form the connective tissue of cloud security, shaping how workloads communicate while enforcing boundaries that contain risk. Their purpose is to constrain traffic to legitimate paths, inspect flows for malicious content, and uphold the principle of least privilege across environments. In cloud architectures, where networks are largely virtual and elastic, these controls replace the physical firewalls and appliances of traditional data centers with software-defined equivalents that must be just as disciplined. Segmentation divides networks into distinct trust zones, firewalls scrutinize flows at multiple layers, and microsegmentation provides granular enforcement between workloads. Together, they create a layered defense strategy, ensuring that even if one control is bypassed, others stand ready to detect or block malicious activity. Understanding these mechanisms is central to mastering cloud security, because networks remain the channels through which attackers move laterally, exfiltrate data, or launch denial-of-service attacks. Segmentation is the practice of dividing networks into smaller zones, each governed by distinct access rules and trust assumptions. In traditional models, this might mean separating production from development or databases from web servers. In cloud environments, segmentation takes the form of virtual networks and subnets that isolate workloads logically. The value of segmentation lies in containment. If an attacker breaches one zone, segmentation prevents them from automatically traversing into others. For example, isolating critical financial systems from general-purpose application workloads ensures that compromise of one does not cascade into another. Effective segmentation aligns with business functions, regulatory boundaries, and sensitivity levels, ensuring that traffic only flows where justified. Without it, networks become flat landscapes where attackers can move freely once inside. With segmentation, they become structured environments where movement is constrained, monitored, and controllable. Virtual networks and subnets are the primary constructs for implementing segmentation in the cloud. A virtual network defines an isolated address space, while subnets partition it into smaller ranges for routing and management. These logical boundaries determine how workloads communicate, both internally and externally. Routing rules within and between subnets allow administrators to define permissible traffic paths, such as restricting front-end servers from directly accessing databases. Subnets also support the application of specific security controls, like network access control lists or routing tables, tailored to the sensitivity of their workloads. This structure provides both organization and security, giving administrators fine-grained control over connectivity. For example, a subnet hosting internet-facing services may allow inbound web traffic but deny outbound database access, while an internal subnet may do the reverse. Virtual networks and subnets thus serve as the scaffolding on which all other network controls are built. Route tables and their propagation settings extend segmentation by explicitly defining how traffic is allowed to flow between subnets and networks. By default, cloud platforms often permit broad connectivity, but customized route tables refine and constrain these paths. Administrators can enforce specific failover behaviors, directing traffic to redundant services during outages, or limit connectivity by excluding unauthorized routes. For instance, a route table might allow front-end servers to reach a load balancer but not back-end management systems. Propagation settings control how dynamically learned routes are distributed, preventing accidental exposure of sensitive paths. Misconfigured route tables are a common source of unintended access, sometimes opening connections that bypass firewalls. By carefully managing these rules, organizations ensure that traffic moves only along defined, secure pathways. Route tables transform abstract segmentation into practical enforcement, bridging the gap between address spaces and actual traffic flows. Stateless network access control lists, or ACLs, act as gatekeepers at the subnet boundary, filtering packets based on explicit allow and deny rules. Unlike stateful controls, ACLs do not track connection context. They evaluate each packet individually. This simplicity makes them efficient for broad filtering but requires precise rule management. ACLs can block known malicious ports, restrict protocols, or enforce one-way traffic flows. For example, an ACL might allow web traffic into a subnet but deny outbound connections on non-standard ports. Because they are stateless, ACLs require administrators to define rules for both directions of communication. They provide a foundational layer of defense, stopping obvious or unauthorized traffic before it reaches deeper controls. While not sufficient alone, ACLs contribute to defense in depth by narrowing exposure at the earliest possible stage of packet handling. Stateful security groups operate at the workload interface, offering connection-aware filtering for ingress and egress traffic. Unlike ACLs, security groups maintain context, automatically allowing return traffic for established connections. This makes them more intuitive for managing server or instance-level access. For example, a security group might permit inbound HTTP requests on port 80 while automatically allowing the corresponding outbound responses. Egress controls can restrict workloads from reaching unauthorized destinations, limiting the blast radius of compromised instances. Because they attach directly to workloads, security groups enforce rules at the point of contact, providing granular protection. Mismanagement, however, can lead to overly permissive configurations, such as allowing inbound access from all sources. By applying the principle of least privilege, administrators ensure that security groups remain precise tools for controlling interactions rather than open doors to sensitive workloads. Virtual firewalls provide a centralized mechanism for enforcing complex network policies, often with features beyond basic filtering. They support deep packet inspection, intrusion detection, and network address translation, making them versatile for shared services. Unlike distributed controls, virtual firewalls act as choke points, where traffic can be inspected thoroughly and policies enforced consistently. For example, all outbound internet traffic from a cloud environment may be routed through a virtual firewall that scans for malicious payloads and applies data loss prevention rules. Centralized logging and reporting enhance visibility, supporting both security operations and compliance. While they cannot replace distributed enforcement like security groups, virtual firewalls complement them by offering depth where inspection and centralized governance are necessary. Their presence ensures that critical flows are scrutinized and controlled before leaving or entering the environment. Private endpoints and service endpoints reduce reliance on the public internet by enabling access to managed services through private network paths. Instead of routing traffic over public addresses, private endpoints allow services such as databases or storage to be consumed within a virtual network. This significantly reduces attack surface, preventing exposure to internet-based threats. Service endpoints provide similar benefits by extending private network connectivity to provider-managed services. For example, instead of accessing a storage bucket over a public URL, workloads can use a private link that never leaves the provider's backbone. These options align with zero-trust principles, minimizing exposure and enforcing stronger control over how services are reached. They also simplify compliance by ensuring that sensitive traffic avoids public infrastructure. Private and service endpoints transform cloud services into internal components rather than external risks. Web application firewalls, or WAFs, specialize in protecting HTTP applications from common injection and abuse patterns. They act as filters for inbound web traffic, detecting malicious payloads such as SQL injection attempts, cross-site scripting, or command injection. WAFs can also enforce rules on request size, headers, and input validation, reducing the likelihood of exploitation. For example, a WAF may block suspicious queries containing SQL keywords from reaching a web server. While they do not replace secure coding practices, WAFs provide an important compensating control, catching attacks that slip through application defenses. Their ability to adapt through managed rule sets or custom signatures allows organizations to respond quickly to emerging threats. Positioned at the edge or behind load balancers, WAFs ensure that web applications remain resilient against one of the most common attack surfaces in cloud environments. Distributed denial of service protections address one of the most disruptive threats to availability: volumetric flooding. Cloud providers often offer built-in DDoS mitigation at the edge, absorbing massive amounts of traffic before it reaches customer environments. These services use techniques such as traffic scrubbing, rate limiting, and anomaly detection to distinguish malicious floods from legitimate surges. For example, a sudden spike in traffic to an e-commerce site during a holiday sale should be allowed, while a bot-driven flood should be blocked. DDoS protections ensure that workloads remain available even under hostile conditions, preserving customer trust and business continuity. Without them, applications exposed to the internet remain vulnerable to attacks that require little sophistication but cause significant damage. Integrating DDoS protection is thus not optional but a necessity in any cloud environment where availability is mission-critical. Service mesh policies extend network control into the east-west traffic that flows between workloads inside a cluster or microservices architecture. Traditional firewalls focus on north-south traffic entering or leaving environments, but internal communications also need governance. Service meshes provide this by embedding security features such as mutual TLS for encryption and authentication, as well as fine-grained authorization checks. For example, a service mesh may enforce that only the front-end service can communicate with the back-end API, blocking all other requests. These controls reduce the risk of lateral movement, ensuring that compromised services cannot freely interact with others. Service meshes also provide observability, logging interactions at the application layer. By shifting network control closer to workloads, service meshes align security with the dynamic, service-oriented nature of cloud-native architectures. Network address translation enables private subnets to reach external services without exposing workloads directly to the internet. Outbound connections appear to originate from a shared NAT gateway, masking individual instance addresses. This provides both security and scalability, allowing many workloads to share a limited set of public IPs. NAT also supports policy enforcement, as outbound traffic can be funneled through inspection points. For example, a private database server may need to download patches from the internet but should not be directly reachable. A NAT gateway enables this controlled egress. However, administrators must balance convenience with oversight, as uncontrolled NAT can obscure accountability. By coupling NAT with logging and policy, organizations ensure that outbound access remains both functional and auditable, preventing it from becoming a hidden pathway for unauthorized communication. Domain name system policies extend control into name resolution, steering how workloads translate hostnames into addresses. Split horizon DNS allows different answers depending on the request's origin, ensuring that internal and external queries resolve appropriately. Policies can also block resolution of unapproved domains, constraining egress at the name level rather than relying solely on IP addresses. For example, preventing workloads from resolving known malicious domains helps block command and control attempts. DNS logging provides valuable visibility, revealing which services workloads attempt to contact. By treating DNS as a control point rather than a background service, organizations gain both preventative and detective capabilities. In cloud environments, where services often rely heavily on DNS, governance at this layer provides an efficient way to enforce policy and detect anomalies without intrusive traffic inspection. Traffic mirroring provides administrators with the ability to create governed copies of network flows for deep inspection and forensic analysis. This feature allows security teams to analyze suspicious patterns without interrupting production traffic. For example, mirroring traffic from a sensitive subnet to an intrusion detection system enables real-time monitoring for anomalies. Privacy and compliance considerations are paramount, as mirrored traffic may include sensitive data. Policies must govern what is mirrored, who can access it, and how it is retained. Done responsibly, traffic mirroring strengthens visibility and investigative capabilities, providing ground truth during incident response. Without it, organizations may be forced to infer activity from logs alone, missing subtle attack indicators. With it, they gain a microscope into network behavior, essential for high-assurance environments. Flow logs provide another cornerstone of visibility, recording metadata about network traffic such as source, destination, ports, and whether packets were allowed or denied. These logs create a rich dataset for anomaly detection, performance monitoring, and compliance reporting. For example, unexpected outbound connections to unfamiliar destinations can indicate malware activity, while repeated denies may signal a misconfiguration or probing attempt. Flow logs are not full packet captures but strike a balance between detail and scalability, enabling analysis without overwhelming storage. Correlating flow logs with workload telemetry and firewall events creates a holistic picture of network activity. This visibility is crucial not only for detecting threats but also for proving to auditors that controls are working as intended. Flow logs transform network activity from an opaque process into an observable and governable domain. Microsegmentation represents the finest level of network control, enforcing policies between individual workloads or even processes. Unlike traditional segmentation, which separates large zones, microsegmentation defines traffic rules at the granularity of specific applications or services. This dramatically reduces opportunities for lateral movement, as compromised workloads cannot freely communicate with unrelated peers. For example, microsegmentation can ensure that an application server only talks to its database on a defined port, blocking all other traffic. This approach aligns with zero-trust principles, assuming that every workload must prove its legitimacy before communicating. Implementing microsegmentation requires careful planning and automation to avoid overwhelming complexity, but the payoff is strong containment. In cloud environments where workloads are ephemeral and highly distributed, microsegmentation provides a dynamic and scalable way to enforce least privilege networking across the fabric of services. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Zero Trust architecture reshapes how organizations think about network security by discarding the assumption that anything inside a perimeter is inherently trustworthy. Instead, every request is continuously verified, using identity-aware checks that consider who or what is making the request, from where, and under what context. Applied to networks, ZTA means that access decisions are not based solely on IP addresses or subnet locations, but on authenticated and authorized identities. This reduces reliance on traditional segmentation alone, layering verification directly into traffic flows. For example, a developer connecting to an internal API may have to re-authenticate with multi-factor tokens, even when working from inside the corporate network. Zero Trust enforces the principle of least privilege dynamically, ensuring that compromised devices or accounts cannot freely move laterally. It represents a cultural as well as technical shift, where constant verification replaces implicit trust as the norm for network access. Identity-aware proxies and secure access service edge solutions extend Zero Trust principles by gating user and device access to internal applications. Instead of relying on VPNs that grant broad network access, an IAP validates the identity of a user and their device before brokering a connection to a specific application. Policies can enforce device posture, such as requiring updated antivirus or encrypted disks before access is allowed. These tools provide visibility into who accessed what, when, and from where, offering far more granularity than network tunnels alone. For example, a remote employee may access the company's HR application through an IAP, with all requests logged and tied to their identity. This reduces the blast radius of compromised credentials and ensures that access is always contextual. In modern cloud environments, identity-aware access becomes an essential complement to segmentation and firewalling. Egress filtering policies control the outbound traffic leaving cloud environments, preventing workloads from communicating freely with unapproved destinations. Without restrictions, compromised workloads can exfiltrate data or connect to command and control servers undetected. Egress filters define allowable domains, networks, or protocols, ensuring that only sanctioned communications occur. For example, an application server may only be permitted to contact its database and update repository, blocking all other internet-bound connections. These filters also support compliance requirements by preventing accidental data transfers across geographic or regulatory boundaries. Enforcing egress policies at gateways and workload interfaces provides layered protection, reducing the likelihood of unnoticed leaks. By treating outbound traffic with the same scrutiny as inbound, organizations close a critical gap in network defense, ensuring that compromised workloads cannot silently send data beyond their trusted boundaries. Layer 7 controls elevate firewalling beyond ports and protocols by inspecting the content and context of traffic at the application layer. These controls enforce rules for HTTP methods, headers, and content types, detecting and blocking malicious or non-compliant requests. For example, a Layer 7 firewall might block suspicious POST requests, attempting SQL injection, or restrict allowed file types and uploads. Unlike lower-level controls, which cannot discern intent, Layer 7 firewalls provide visibility into how applications are being used and misused. They also allow for more nuanced policies, such as rate-limiting specific API calls or enforcing strict content validation. This depth of inspection is particularly valuable in cloud environments, where applications are frequently exposed to the internet. By scrutinizing requests in detail, Layer 7 controls help ensure that application pathways remain functional but not exploitable. Border Gateway Protocol controls extend network security to the edges of hybrid and multi-cloud environments, where routing decisions shape connectivity. BGP is powerful but vulnerable, as incorrect or malicious route advertisements can redirect or black hole traffic. Controls include preferring known safe routes, filtering advertisements to prevent propagation of unauthorized prefixes, and monitoring route stability. For example, filtering ensures that a cloud environment does not inadvertently accept a route hijack that sends sensitive traffic through an untrusted network. Hybrid architectures benefit from BGP resilience, allowing failover between providers or data centers when primary routes fail. By governing BGP, organizations reduce exposure to one of the Internet's most subtle but impactful risks: insecure routing. These practices transform routing from a background operation into a managed, auditable control that directly affects trust in cloud connectivity. IPv6 planning introduces new challenges and opportunities for cloud networking. With its vastly larger address space, IPv6 eliminates the need for widespread NAT, but also complicates segmentation strategies. Neighbor discovery replaces traditional ARP, requiring new security controls to prevent spoofing. Dual-stack operations, where IPv4 and IPv6 run in parallel, demand careful governance to ensure policies are consistent across both protocols. For example, a firewall rule applied to IPv4 traffic must have an equivalent for IPv6 to avoid creating bypasses. IPv6 also changes visibility, as workloads may receive multiple global addresses by default, expanding their exposure. Proper planning addresses subnet sizing, routing design, and security rules tailored to IPv6's mechanics. Treating IPv6 as an afterthought creates blind spots. Treating it as a first-class citizen ensures that future growth does not outpace security controls. Overlapping address spaces remain a persistent challenge in multi-cloud and hybrid deployments. When two networks use the same private ranges, connectivity between them can break or create unpredictable routing. Remediation strategies include renumbering networks, deploying translation gateways, or applying boundary NAT designs. Each approach has trade-offs. Renumbering provides long-term clarity but may be disruptive, while translation preserves function but adds complexity. For example, a merger may join two organizations that both use 10.0.0.0/8 for internal addresses, requiring careful reconciliation. Overlapping addresses not only complicate connectivity but also undermine security monitoring, as flows may appear ambiguous. By planning remediation early, organizations prevent operational friction and preserve the integrity of segmentation and logging. Addressing overlap proactively ensures that scaling into hybrid and multi-cloud environments does not introduce hidden risks. Policy as code represents a transformative approach to managing network controls, embedding rules directly into code repositories and pipelines. This practice validates policies before deployment, reducing human error and ensuring consistency across environments. Continuous reconciliation ensures that runtime configurations remain aligned with approved baselines, automatically correcting drift. For example, a misconfigured security group that accidentally allows wide-open access could be detected and fixed automatically. Policy as code also integrates with version control, providing traceability for who changed what and when. This shifts network governance from reactive configuration management into proactive, automated assurance. By codifying intent, organizations reduce reliance on manual reviews and create defenses that evolve alongside development. Policy as code exemplifies how modern infrastructure combines agility with accountability, turning network security into a discipline of repeatable engineering. Change management remains essential in environments where network updates carry significant risk. Even with automation, approvals and coordinated rollouts prevent mistakes from cascading into outages. Best practice involves peer reviews, scheduled maintenance windows, and documented rollback plans. For example, introducing a new firewall rule might be staged in a test environment, rolled out incrementally, and monitored closely before full deployment. Rollback paths ensure that if a change introduces unintended consequences, recovery is quick. While some view change management as bureaucratic, in high-risk domains it provides assurance that network updates are deliberate and reversible. In cloud contexts, where changes can be applied globally in seconds, discipline is even more important. Effective change management balances agility with safety, ensuring that innovation does not come at the expense of availability or trust. Segmentation validation confirms that network controls work as intended, preventing a false sense of security. Techniques include synthetic probes, which simulate traffic flows to test access, and packet captures, which verify whether traffic is blocked or allowed. Policy checkers analyze configurations against desired baselines, flagging inconsistencies or overly permissive rules. For example, a probe might test whether a development subnet can reach production databases, confirming that segmentation policies block unauthorized paths. Validation is continuous, as networks evolve constantly and assumptions may drift. By testing enforcement actively, organizations replace guesswork with evidence. This assurance is critical not only for internal trust, but also for compliance, where auditors require proof that segmentation and firewall rules are effective. Validation transforms controls from paper policies into demonstrated protections. Administrative access paths must be tightly controlled, as they provide the keys to managing network controls themselves. Best practices include confining access through hardened bastion hosts, enforcing just-in-time elevation for privileged tasks, and recording sessions for accountability. For example, an engineer updating firewall rules would first authenticate through a bastion, request temporary privileges, and have their actions logged. This reduces the risk of compromised accounts being used to manipulate controls while also deterring insider misuse. Administrative paths are often targeted by attackers because they provide leverage over entire environments. Isolating and monitoring these pathways ensures that powerful privileges are exercised responsibly. In effect, administrative controls become controls over the controllers, reinforcing trust in the governance of network security. Monitoring ties together the signals from flow logs, firewall events, and workload telemetry to detect violations and anomalies. Correlation across these sources provides context that individual feeds cannot. For example, flow logs may show repeated denies from a suspicious IP, while workload telemetry reveals unusual CPU spikes, together suggesting an attack. Monitoring not only detects threats, but also validates policy effectiveness, showing whether rules are operating as intended. Centralizing monitoring ensures consistency and simplifies investigation, while automated alerting enables timely response. In modern environments, monitoring is not optional. It is the verification layer that makes all other controls meaningful. Without it, networks become opaque, leaving organizations blind to both successes and failures of enforcement. Evidence generation supports both compliance and internal assurance by producing tangible records of network governance. Artifacts include rule sets that define intent, change records that show accountability, and test results that validate enforcement. These artifacts map controls to regulatory frameworks, demonstrating that requirements have been met. For example, evidence might show that a PCI environment has strict segmentation, validated by regular testing, with all rule changes documented. Evidence generation also strengthens internal trust, providing leadership and auditors with confidence that policies are not only written but also applied. Automating evidence production reduces burden and ensures consistency, embedding compliance into routine operations. By treating evidence as a product of security rather than an afterthought, organizations demonstrate maturity and resilience in their network governance. Anti-patterns in network security illustrate the dangers of neglect or convenience. Any-to-any rules, which allow unrestricted traffic, effectively erase segmentation and create flat networks. Unmanaged public exposure leaves sensitive workloads accessible from the Internet without proper protections. Stale exceptions, granted temporarily but never revoked, accumulate into hidden vulnerabilities that attackers can exploit. These anti-patterns often emerge from pressure to move quickly, or avoid friction but carry long-term consequences. For example, leaving a test system exposed for convenience may become the entry point for a breach. Recognizing and avoiding these pitfalls is as important as implementing best practices, as small shortcuts can undermine entire architectures. Anti-patterns remind us that security is as much about discipline and culture as it is about technology. For exam purposes, network controls are tested through the lens of least privilege and layered defense. Candidates must know which controls apply at which layers. For example, distinguishing between subnet ACLs, workload security groups, and application-level firewalls. Exam questions may also probe understanding of microsegmentation, zero trust, and monitoring as mechanisms for reducing lateral movement. The emphasis is not just on identifying tools, but on applying the right control in the right context, with verifiable assurance. Understanding both the strengths and the limitations of each control demonstrates readiness. For learners, the key is to see the network not as a monolithic perimeter, but as a fabric of layered, context-sensitive defenses that together enforce governance and resilience. In summary, deliberate segmentation, complementary firewalling, and microsegmentation work together to create secure and observable network paths. Route tables, ACLs, and security groups define boundaries, while firewalls and WAFs inspect traffic at multiple layers. Private endpoints and service meshes reduce exposure, and monitoring with logs and evidence ensures accountability. Zero trust and policy as code extend these principles, making access identity-aware and automation-driven. Avoiding anti-patterns and validating enforcement maintain integrity over time. For professionals, mastering network controls means recognizing that no single control suffices. Security emerges from the integration of many mechanisms, each reinforcing the others. By applying this layered approach, organizations ensure that cloud networks remain not only functional, but also resilient against the evolving threats that target their pathways. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.